Okay, so what we have here is a fractional knapsack problem, and we're going to solve it for a knapsack capacity of 18. And we're going to solve it for these items on the left here. So we have 7 items, each with, and we've got their value and their weight all written here. Now the way we solve this is we break the knapsack problem down into sub-problems, and we use, this is dynamic programming, to find the best solution. So what we do is we start by initializing our sort of array to a row of zeros. Now this is for not taking into account any items, so we've got none here. So we're saying that for each knapsack size, if we don't take into account any items at all, then the best value we can have is 0, obviously. Okay. So this program was written by Pete Sutton, and it's an awesome way of demoing the knapsack problem using dynamic programming. So what we're going to do is we're going to step through this problem and see how it works. And we've initialized our arrays to 0. So on the first step, what we do is we take a knapsack problem, a sub-knapsack problem, like a mini knapsack problem of capacity 0, and we try and fit this item into it. This item with a value of 12 and a weight of 4, and it won't fit in. This is the first check that we make. Basically there are 3 things that we need to check. The first is that the item will fit in, the item will fit in to this capacity, and it won't, so it's just 0. The same for 1, 2, 3, 1, 2 and 3. You see, we filled in those rows. Now for 4, our first check gets met. And the first check is, if the item will go in, then try and fit it in, or don't try and fit it in, okay, as we'll see later. So it will fit in, so which is the best value, fitting it in or not fitting it in? Well, of course, fitting it in is the best value, because if we have a knapsack of size 4 and we're only taking into account this item, then that's the best solution to put it in, to get the best value. Now, how's that actually computed? Well, what the computer actually does at this stage, and it never did this before because it couldn't fit an item in, what it does is it says what's best to fit the item in or not to fit the item in. So it says, well, if we do fit the item in, then we will have this knapsack of 4, and we will fill up 4 blocks of this space, and we will be left with 0 blocks. So what is the best solution for 0 blocks? Well, it's, and with the other items, well, it's 0. Okay, so it's 0, this highlight here, and we add that to our value of our item that we are going to fit in. So 0 plus 12 is 12. So that's one value. That's if we take it, we've worked out this value of 12. If we don't take it, then we solve the problem for the same capacity, but for the remaining items, and there are no remaining items, so we'd look at this none, we say 0. So that's if we don't take it, we get 0, and if we do take it, we get 12. So 12 is the best solution, and we can see in our keep matrix down here, then we have the number 1 indicating that we should keep this item for a knapsack capacity of 4. We fill that in there. So that might sound very obvious. Obviously, if we're taking into account one item for such a small knapsack size where it will fit in exactly, the best solution is to take that item. But we'll see that this is the step that the computer makes at every or most of the steps where you can fit an item in. So this is key to the rest of the table, and we're going to see that. So moving on, we increase the knapsack capacity to 5. We try and solve that problem, and each cell we're solving a mini knapsack problem. Ultimately, we're going to solve this cell down here, which is the knapsack solution to a knapsack of size 18, which is the size that we want, and including all the items in the table. That's what we're going to work up to. So now we work up to our sub-problem of 5, and it's still 12 because we because we just have a load of space, basically. We have a load of space, and that space of size 1, basically, because we filled this in of 4, weight of 4, but we've got a 5. So the space left is 1, and that's what the best we can do with a space of 1 so far with the other items, 0. Okay, so it's always 12 plus 0, and that's going to be the case for the rest of the table, because we're not taking into account any of the other items. So we move on to our second row. Now we're looking at 2 items. So in the first column, we still have a capacity. We still can't fit anything in with a capacity of 0, obviously. So the first check is, can we fit this new item, our current item, into the knapsack on its own? On its own, right? No, we can't, because the capacity is 0. Okay, so let's and then what we do is we take the value of the row above it. We take this one. Okay, because we can't fit this in, we say, well, we'll solve the solution for the other items, the ones that are left, for the same size. And we do that for 1. We look, because we can't fit it in, we look at this value. We do that for 2, because we can't fit it in, we look at that. The same for 3, we look at this one. And for 4, we can't fit it in, so we take the value for this. For 5, we still can't, and we take the value here. Now for 6, we can fit it in. So what we're going to do for this cell here is we're going to say which is best. We either put it into the knapsack and fill the rest of the space, or we don't put it in and we fill the knapsack using another means, right? So if we do put it into the knapsack, if we do put it into the knapsack, then we will have a space of 0 left, because we have a capacity of 6 and a weight of 6 here. So we'll have a space of 0 left. So we do the value of the current item that we're going to just put into that, and we add it to the space that's left for the other items, which is 0. And we would get a total of 10, right? Because 10 plus nothing is 10. So that's if we take it. If we don't take it, then we consider the case for the same knapsack capacity size for the other items in the list, which are these, right? And we look at this cell, just the cell above it, because this is the same knapsack problem for the other items. And we get a value of 12, so when we're comparing that to the 10 that we worked out before, we see that 12 is bigger, so let's not take it. Let's use the value up here. So that's what it is. I've just stepped on there, and we put our 12 in, and you can see down here in our keep matrix, we have 0. So that's what it's done there at this step stage. And this is what happens again for the capacity of 7, capacity of 8, and the capacity of 9. At the capacity of 10, what we're doing is we're saying, will this item, again we're doing our check, we're saying, will this item fit in the knapsack on its own? Yes, it will. So, which is the best case? Do we put this item in and solve this sub-knapsack problem, or do we not? And this is the key thing. If we take this item, what we're left with is another knapsack problem. We're left with the problem for a knapsack of capacity 4, because we have this capacity of 10, we put this item in, and that item has a weight of 6. So we're left with a knapsack of capacity of 4. That's our space. It's the space that's left. So how are we going to fill the space? Well, we've got to use the other items, which are these, and we got to use the capacity of 4, which is this. It's 12. Okay, so this is the column. Hopefully you can see the cursor. It's a knapsack with capacity 4, and with these other items, it's 12 is the best. So we do 12 plus this 10 is 22, and that goes in there. And these are the checks that the computer is taking into account. Sorry, I should have also said, sort of skipped ahead. And it also checks, well, what if we don't take the item? Well, if we don't take the item, we solve it for the same problem. And for the other items, which are these,